You don't have a class now? Oh, okay.
Hi, Paul.
Yeah, some students do come in early, don't they?
Yeah.
I get here like at 7 and students are already showing up.
Yeah. We start every day.
Is that because architecture students are lazy or what? We just can't get them here?
The cafes,
Right.
happy hours go through.
Gotta get that coffee.
Yeah, exactly.
There's Paul. Can you hear me?
I sure can. Can you hear me?
Can't hear you, Paul.
You can't?
Can you hit unmute me? Where is it?
How about now? No?
You see this?
Where?
Turn your volume up.
Where,
It does
no, but
really
where were
cool
you down
things.
here? Because I was up.
Click on your volume.
Oh, down here.
No, it's Wi-Fi. This is volume.
Can you hear me, Paul?
I can hear you. Can you hear me?
Wow.
Yeah, I'm getting to. I'm getting that. I'm an intern on technology.
I understand.
Oh, thanks. Anyways, just to give everybody an update, I'm going to turn this around so you can see the crowd.
Give everybody where Paul and I met, both lecturing
At the university in Singapore. Well, that's how far back we go. Then it turns out that I was working in Detroit, and Paul turns out to be in Detroit. So it's like, wow, just everything just kind of came together. Stars aligned. Can you see the group?
I can. Hi. Can you hear me all right?
Yeah, I think so. Yeah. We also have somebody visiting us this morning from our electrical department. So he's a faculty member and professor of electricity. Nick.
Hey, Paul.
Hi.
So he's going to ask you the tough questions.
Please, you guys are in Wisconsin, right? Or in Minnesota?
No, we're in Minneapolis.
Minneapolis.
Yeah, we're in a, what is the day? Minus 25 degrees wind chill.
All right.
What's it like in Detroit?
You're not scaring me. It's a little warmer than that, though. We're probably in the 20s today.
Excellent. Well, I've given everybody your website and actually downloaded some of the documents, your frequently asked questions, and your technology review. So, and also, I don't know if you saw this, but on your website, there's a bunch of links to videos. And there's a couple cool ones with Austin DC Power.
That's right.
Some of my students thought that was you.
Oh, really? I can tell you who that guy is. He is actually the highest paid Trump impersonator in the country right now. His name's John DiDomenico. And whenever you see a Trump impersonator for pay, it's usually him. And
wow.
he moonlights as Austin DC Power.
Well, he tricked me for a while. He's got it down pretty well.
Yeah, he's quite skilled. All right. Well, shall I just tell you what I think the story of our technology is, and we can open it up for questions and see where the dialogue takes us?
Yeah, please.
Well, thanks. It's nice to talk to you virtually. I like talking to students and people in school that are interested in renewable energy systems, alternative technologies for electrical power distribution, and how we use energy generally. Our company started in Long Island, New York, because our co-founder was a division scientist, a division head scientist at the Brookhaven National Labs. Brookhaven is one of the now 8 federal labs that does pure research into energy. That used to be 7, but they added the International Space Station as one of the labs now. Anyhow, when Bill was working in the 90s on thin film solar, which at that time was an exotic endeavor, he kept on coming back to the fact that in his experimentation with thin film as a energy resource, he was always having to really test it in AC load, as they generally appear to dominate. And it was in that process that he came to appreciate that really most of the load, which is to say how we consume electricity, was going electronic. And everything electronic was ultimately consuming direct current. So he did some work in establishing some intellectual property, some patents around DC power systems, and that was the beginning of our company, Nextek Power Systems. So a lot has changed since we started. In the early days, an installed watt of solar would cost you around $13, and now that's generally around $1. So there's been a massive reduction in the cost, and that has been largely due to material science and better and better technology getting into the solar panel, but also into the balance of system, which for us means the DC power distribution system in a building as opposed to the conventional AC or alternating current system of power distribution in the building. So back in the 90s, we went after lighting. This is before LEDs were dominant as they are today. Are those LED 4-foot fixtures over your head there in your room?
I don't think so.
Oh, those are T8 fluorescents? Okay. Well, they because the payback for LED light sources has gotten so short that really, if you're going to touch those lamps again, to either replace a burned out lamp or to replace a ballast, which is the electronic device that drives the lamp, the cost of doing that work is heavily tilted towards the value proposition of LED. And I would tell you that if you went to Light Fair, you know, the big trade show for the lighting industry, you would discover really no fluorescent light sources anymore. The forward-looking menu for all lighting, at least in the United States today, is LED. And so that played very nicely into our business plan because we're looking for intrinsically DC load. A good example, everyone's got a laptop on their desk or in their life, I'm sure. Nearly all of those laptops today have an external power supply, you know, like one of these for an Apple, or the black power supply that you'd have for a Dell or an Acer or Hewlett Packard. All of those are power converters. So like in lighting, where we've gone after the power conversion, the unnecessary power conversion of AC to DC in the light fixture, we're also trying to eliminate that in your charging devices, your personal computers, all of the electronic components that go into video cameras, security systems, control systems and sensors. Do you have an occupancy sensor in that room that turns things on and off when you leave?
No.
No. You are not up to code.
We're just the College of Technology here.
Well, I'm going to have to send you a technology care package. Wait, what department are you in? I demand to know.
What did he say? Yeah, this is the architecture department.
Okay. All right. Well, then tell
And
me.
this is a fairly old building too, so I'm not sure when it's being upgraded.
Well, we're gonna. You know what we should do is we should. How big is your building?
Yeah.
How big is it?
How big is
How big is the building? Anybody know? Well, it's, how many stories is it? It's 300,000?
It might be 300,000.
300,000 square feet?
Holy moly! And it has an undetermined building management system in terms of controls for lighting and heating and that kind of thing.
Yeah.
Our facilities management just turned over last year. So there's a plan to updating rooms. Parts, some of them have the current energy code and
Yeah, I'm sorry, I can't hear the person speaking.
sorry, yeah, this is Nick. We had a turnover in our facilities management. So they're cycling through a 5-year plan to update to the energy code. For example, the HVAC system really needs to be revamped, but everything costs money.
Okay, I'm going to see if I can get my bandwidth increased so I can get a chance of hearing you better.
You can hear me though, right?
Yeah, I can hear you.
I'm sitting behind the computer.
It's the magic of sound waves, I guess. Well, how great that you're in a space that's going to be renovated soon.
Yeah.
That would be the cheerful way of looking at it. And I can say that with some confidence because regardless of the state incentives for educational building, the value proposition of going to controlled LED systems is such that even without the incentive, it makes financial sense to execute the upgrade. So that'd be fun for me if you guys have drawings with a reflected ceiling plan or can produce the same. It might be fun to do a layout for a floor in the building and kind of talk about what the differences are between conventional practice and what's happening now in low voltage DC systems. You will shortly hear, I hope, when we press release it, a new application for these low voltage DC systems that's in the receptacle. I'm quite sure that all the receptacles in your room are offering AC only at the wall. You may see at the airport an embedded USB-A port that you could plug a phone charger into. I doubt those have crept into your building. But part of what we're now delivering with our DC system is not just lighting and control, but also DC outlets. And not DC outlets that take AC and convert it at the point of use, but AC outlets or DC outlets rather that are connected to a larger bus architecture that shares direct current around the building. So instead of doing all of these conversions from AC to DC, which in the room you're sitting, I would expect there to be, I don't know, 80 or 100 AC to DC conversions, and we would reduce that number down to 2 or 3.
Yeah.
And the reason to want to do that is that each one of these conversions is lossy. You lose power in its conversion, and it's these days unnecessary.
Yeah, and they also produce heat.
They also produce heat, which I guess
Hot right now.
if you're cold, that might seem like a benefit, but it's fleeting because overall, what with the tightness of buildings today, you're going to want less unintentional heat from power and conversions, and make instead your HVAC system designed around human comfort, not incidental.
So our project, Paul, in Belize with this DC island could be something which could kick off maybe taking our floor. This is the third floor of the building, and use this as a guinea pig or a lab, a case study. So I'll research that with Nick and see what we can come up with for you.
It's everything downstream from the power supply is class 2 power, so it's below the shock hazard, below the startle hazard, below the fire hazard. So it is, in that sense, ideal because people can work with the wiring and the devices without fear of hurting themselves.
Mm-hmm.
But where I was going with the DC outlets, one of our customers is Kaiser Permanente, the largest managed healthcare system in the United States out in California. And they've adopted our DC lighting and control system and are now going to be our second sizable customer for these DC outlets. So you'll be able to take your power cord without a converter in it and plug it directly into the DC distribution at the wall receptacle.
So that was one of my questions. So you can buy a cord for your laptop or cell phone directly to a DC outlet, correct?
Yes, you can.
I haven't found it. Has anybody seen those? Are they commercially available?
They are. You really have to find them online because the DC outlets are not as ubiquitous as we hope they'll become. But they're out there. We just shipped 350 of them to a really interesting building. I invite you guys to take a look at building.agu.org. AGU stands for the American Geophysical Union. They did a spectacular urban retrofit of their office building, which is now net zero energy in Washington, D.C. And they've done a wonderful blog that you can go back and see the different solutions they brought to the party at building.agu.org.
That's one of your case studies on your website, right?
I hope so.
Yeah, I think it is.
It's a good one. So any suspicion about batteries and solar, or is the mood of the crowd to be interested in incorporating those systems in yours?
Well, our goal, as I've showed you or talked to you about, is that we want this island to be as DC powered as possible, because we're really far away from the mainland. There's no way we're going to get grid power, and right now the facilities on the island are all powered by photovoltaics. They're looking at wind turbines right now, but they haven't had success with wind turbines, primarily because they say the ones they purchased were cheap and not effective.
Yeah.
But right now it's all PV. So obviously we're looking at trying to reduce our electrical demand to reduce our PV requirements. And so, as I indicated to you, we don't plan on having any televisions or major appliances in the facilities. And as you know, the building right next to you, right on campus there, Next Energy, is a Bosch appliances. It's got a DC refrigerator, DC. Do they have a DC freezer?
No, Bosch does not.
Okay.
We have retrofit refrigeration and freezer products before, and it could be that what you're doing is a big enough order to get the interest of manufacturers of those white goods excited about making them themselves. You know,
okay, so is it a Bosch washing machine and dryer?
The guy at Bosch that I've been dealing with, that my champion there, is on a different project, and I can't really tell where the excitement in that organization is for the DC ready loads.
Okay.
The founder of D.R. Horton, one of the largest home builders in the country, has started a company called Horton World Solutions, which is making hurricane-resistant housing, and they're right at the tip of the spear in terms of working with the major appliance manufacturers to create DC-ready versions of their product.
Okay, yeah, if we could find partners like that, that would really be great.
Yep.
This could turn out to be the first island that's completely DC powered.
That'd be wonderful. We started that Coconut Island off of the coast of Maui, and we wound up with so much motor load that we couldn't really get there. So I'm motivated to help you realize that it's Belize, right? Off of Belize.
Yeah, we're off of Belize. It's about an hour-and-a-half boat ride from Belize City Airport.
Wow. Okay.
Yeah, I'll send you, if I didn't already send it to you, I may have already sent you the brief on the island, its location.
Yeah. No, you did send me the deck. I've been to Belize before, and I've swam the blue hole, but it looks like you have a different blue hole in your island.
No, this is the Great Blue Hole.
Oh, it is? Okay.
Yep.
I didn't feel like it took me that long to get there, but I was younger then.
Yeah, Branson and Cousteau just did a submersible dive down the Great Blue Hole. They had it televised. It was a live feed.
Yeah, it's an amazing. Did you get to dive it yourself?
No, I haven't been down to the Great Blue Hole. But Long Key, our island is about 15-minute boat ride to Great Blue Hole. So most divers stay at Long Key on our island.
Neat.
Yeah, so that's where we're located. It's 650-acre island.
So tell me, do you have any electrical engineers in this group, or is we all talking conceptual at this point?
We're gonna tap into Nick in the electrical department here at the college to help us. But basically, so if we're doing an electrical plan, like if I'm an architect and I'm designing the electrical layout, am I doing a similar layout that I would with DC and AC, or is it completely different?
It's not completely different. There's just some things you have to take into consideration when you're working with DC instead of AC. We would probably recommend you pick a distribution voltage in the 400 volt range for your DC bus. There are some utilities working up at 1,000 volts DC that we're in contact with. There's a big project going on in Puerto Rico right now in the northeast corner that'll probably have a distribution bus up at 1,000 volts. But I think the key is to figure out at what point in your microgrid you're going to bring solar and batteries to the party, whether you expect that to be locally at the buildings or whether you have some broader microgrid approach that you're going to undertake, or both. That's kind of a key decision.
Yeah, that was one of the questions we had. Is it better to have them individual building by individual building systems, or is it better to have a microgrid where, let's say, it's everything centralized?
Yeah, it won't surprise you to hear from me that a decentralized approach it makes more sense.
Okay.
But it could be that, having said that, you wouldn't put all of your eggs in that basket, and instead you'd have some systems that are co-located at the building and still have some strategy for adding solar, for example, to the distribution bus in addition to building integrated PV.
Well, part of the challenge we've got is that obviously we have a limited amount of rooftop area, yeah, right, for PVs to power individual buildings. So we were thinking of doing what a lot of islands are doing right now, which are putting PV systems arrays on barges just offshore.
Yeah, what's the hurricane strategy for that?
The hurricanes that have passed over don't seem to really do much damage to this island because the reef structure, it's an atoll. which basically means that we have over 5,000, is it 5,000? Yeah, 5,000 feet of reef before it actually hits the island. It's the wind force is really diminished significantly by that reef that's out in front of the island itself.
So you would be permanently anchoring a solar field adjacent to the island?
Well, they'd be on barges, so they could be mobile. So we could actually, we could move a barge to the other side of the island, for example, if that's where it was located. But we also plan on having food production and maybe solar desalinization. We plan on using barges a lot because the real estate on the island is really an ecosystem sensitive area. So we don't want to do a lot of land clearing. It's actually against the eco guidelines. So we do, a lot of the structures have to be, in fact, every structure has to be 8 feet off the ground. So everything's still built.
Yeah.
But we can build on water. And the barges obviously make sense because that means we can bring things in from the mainland as well. So I guess the question is, we can't just have this gigantic array of PVs clear-cutted on the island. So that's why we're thinking of them offshore. Now, when I say offshore, that means that they're not that far. I mean, they could be 100 feet, 200 feet from a building.
And are you working with someone on the barge idea?
Yes, ourselves.
Okay. And how about the load schedule? Have you come up with estimates for each building's loads and what comprise that?
We're working on that right now. We're getting pretty good data on the electrical demands of the facility.
Great.
And water. Everything that's requiring electricity, we're coming up with estimates for. So we'll have a good idea of what our demand is. But it would be helpful to know what kind of energy would we be saving by going DC versus AC.
Well, happily, our first costs are often less than conventional systems now. So it often makes sense just because of the first cost and the reliability, the intrinsic reliability of DC systems versus AC systems. So you will likely save on day one, and then depending on the application, we say it's between 10 and 20% in your operating expense in terms of kilowatt hours.
So you're saying 10 to 20% reduction in electrical demand?
Consumption.
Consumption.
For the same demand, we would expect, and again, it depends on what we're measuring ourselves against. But if your loads are going to be largely electronic, you'll have some motor loads, I'm sure. There'll be a high percentage, a majority of your loads will be able to be driven with less power in a DC format. That's what we've shown over and over.
Do you think it's smart to have a what am I looking for? Let's say an AC power rectifier in case we need AC assets?
An inverter, you'd call that. And yes, you probably want to have an inverter around for legacy devices.
Okay.
But generally, you can design them out, has been our experience.
Does anybody have any questions?
I have a question. So we're thinking about using some flexible PV panels to adhere to curved roof surfaces. They look really handy, but they also look like they produce less power than traditional solar panels. Do you know anything about those? Do you ever use them or tell people to use them?
And which panels are you referring to that
These are panels which are built into tent structures that the military uses, for example.
Yeah.
I was talking about global solar PV panels. It looks like it's a big long strip of PV that I could.
It rolls out.
Yeah, exactly.
Yeah, it's a PV roll.
In between the seams of a metal roof.
I see. Okay.
Yeah.
Yeah, those I do know about those. That's called thin film solar when they attach them to tent structures, and they are less efficient and they tend to be more expensive. there's a few famous stories of companies that were started to make that kind of power and have failed commercially in doing so. The government, especially the military, are still customers for that kind of technology, but you know, because they want to have some PV sourcing when they're out in the field. But if you're designing a dedicated facility that doesn't need to move, you're going to get more value for your dollar with a single crystalline or multi-crystalline silicon panel than you will from that telluride technology, gallium arsenide telluride technology, which is what goes into the thin film. So it's cool looking, but it's dramatically more expensive, has a shorter life, and doesn't produce as much energy as a fixed panel would.
Thanks. Anybody else?
Yep. I'm wondering if you could talk about just like physically when we're designing a space for like a microgrid system. Because basically, depending on where our design lands, we'll have this campus where it's like there's one kind of gathering place, like we're just calling it a lodge. Then there's going to be cabanas where students can stay, and then a couple of separate research facilities. All of those could have PV on the rooftops, or the PV is on barges. Are we making these? Are we wiring these all back to a building that houses some kind of power station, and then the power is being fed out of there? Like, wondering if you could talk about just like designing, or how we can approach the design of this.
Yeah, that's a good question, because you really, at the beginning of the project, you're standing at a fork in the road about how much or if it makes sense to directly wire some power generating assets to specific loads instead of having them contribute power to a bus, which would let you share the power generated amongst many loads and not just one. I would imagine that along with your building, you're also probably going to have some covered walkways. Does that sound likely?
Yes.
So those are great opportunities to have your wiring that will share the power and the power generating assets co-located.
Yeah, we typically run all of our infrastructure, our pipes, plumbing, and wiring underneath the boardwalk, so it's accessible. Because remember, our boardwalks are about 8 feet up in the air.
Yeah, that would be great. And that would be the natural location for your bus.
Okay. Did that help?
Yes. And then maybe just a follow-up question. Like, do we need to design a building then that houses some kind of power station? And like, is a battery storage in the same building? And then another question would be like, do we need to worry about heat and distance of that building? Because it's a tropical area, there's a high relative humidity, it's like 80%. So just that structure, is it a huge room? Is it like what is that?
Yeah, this goes back to what we were talking about earlier about how much power infrastructure you want to have at the building site versus supporting the community microgrid. And I expect you're going to have both. You might have battery storage the size of a loaf of bread at a house, which you could get about 1 kilowatt hours worth of battery storage and lithium ion battery pack as big as a loaf of bread. And that would take you quite some time in terms of lighting and communications at a house. But your needs are much greater to support the overall grid. Think of like a rack of server gear in a data room. That would represent maybe 30 kilowatt hours of power that you could use to hold up the distribution bus. And that will have to go into a temperature controlled, humidity controlled space for sure. And the specific requirements of the chemistry you pick are going to be specified for you by the vendor.
Do you have any preference for manufacturers of batteries?
I wish I did. It's been a pain in the neck for us. We've dealt with some great chemistries. I'm most happy with lithium iron phosphate batteries. Those are the ones that seem to have the best safety profile and longevity, number of cycles.
Is that the Tesla Powerwall?
They have lithium phosphate. I don't know that their Panasonic cell was iron phosphate. I think maybe their new supplier is making iron phosphate. But they're around. There are a bunch of suppliers for them. The problem with the Powerwall is that they elected at the end of their development to package it with an inverter and not let you use it to support the kind of battery bank I would expect you to want.
Okay. Yeah, plus there's a backlog, like 5 years or something to get a Powerwall.
Yeah.
Have you heard anything about or used their shingles?
I'm into the Tesla shingles.
Tesla shingles.
I've tried to buy them. I haven't been able to yet.
Yeah, I've tried them on a couple projects and I can't get them.
There you go. So that's all you need to know about that story.
Oh, how about a Tesla car?
Those are sweet, but you will not have one on the island.
We won't have one on the island. Oh man. Do they
No,
make?
but
Yeah, no, we don't. They're not allowed on the vehicles like that aren't allowed. But we are having electric, solar-powered golf carts.
yep,
And one of my
exactly.
questions is, can we use the golf cart as a battery storage?
I'd be very interested in doing that. I've got a proposal right now with the Lawrence Berkeley Labs to do that on an Air Force base for golf cart chargers that are solar assisted. So hopefully we'll win that, and I'll be able to give you some
Okay.
real life experience on it.
Well, even if it's just a basic electric golf cart, we can use that as battery storage, right? In case we have.
Well, they do, of course, carry batteries, but using that battery to charge something other than the golf cart is not what they're designed for. So you would.
So can we run excess PV power that we're not using into the golf cart for storage?
Yes.
I guess you're saying that would work though, because then you can't use that battery for other uses.
Right. Exactly.
Okay. All right.
But you bring up a good point. There's a neat product I've learned about called a Quanta, AQUANTA. They make it's kind of like a Nest for a water tank. So it does a really good job of tracking and assessing hot water use, and you can program it, or it can help you program itself to use your water storage tank as a kind of battery for your hot water needs.
I've got a question. How about, since we're going to have like peak production times, probably in the morning, we're on the east side of the island, I believe. And also, of course, it's solar, so it'll only work in a day. How about a kinetic water battery where we would pump water up into a big tank and use that to produce power for the evening?
Yeah, love that. Unfortunately, the height you need to make that an economic undertaking is about 80 feet. And so you're probably not going to be building that big a tank at that height.
Why is that? Why do you need 80 feet?
Well, it's about the head.
Oh, okay. You're saying about the head. Right. I thought maybe you're talking about the power of pumping it up, but we can use wind power for that.
Right, but you still need a pretty big vessel up there. There's there's a lot of interesting. What's the water temperature down 20 feet? around the island?
We have to go out. We have to go out about 2,000 feet off the reef, off the shore, 2,000 to 5,000 feet, and then it drops about 2,000 feet.
Aha.
It's a huge wall.
And is there potable water on the island, or do you have to make it?
No, we have to make it. So we're using rainwater, solar desal, maybe even going into gray water and black water treatment, purifying it for drinking water.
So, Paul, one of my colleagues here at Nextek is named Wayne Gutchow. I'll send you his contact information. He's been our point person with the IEEE and the IEC around developing world applications for our DC systems. And
Okay.
he's done a couple of different water treatment strategies. And I'll invite you to get in touch with Wayne and have him tell you what he's done to see if there's any of those projects, specifications and dimensions that might be useful for you down in Belize.
Yeah, I mean, one of the systems that our team's found is called, I think it's called WaterGen. It's an air to water
Yeah, that's cool.
technology. Now, I don't know, you know, I think you even know how much electricity it requires, right? It's not a lot.
No. Yeah, Duke Energy has got a bunch of those on pilot. I've seen them. They're really cool.
Yeah, they produce quite a bit of volume for us as well. So yeah, we're looking at a whole bunch of hybrid systems. We're not looking for one thing solving everything. It's going to be hybrid. Are we going to need your power server module, the PSM, in every building?
Well, probably. If you want to have wireless access points, if you want to have lighting and control, and you want to be able to assess the building, the power system's stability and the state of charge of the batteries and whether all the solar is producing, you'll need either my product or something just like it. So I'd say go my way.
So, do you want to explain to everybody about a microgrid versus a nanogrid? I keep hearing about DC powers are called nanogrids now.
Yeah, I don't, you know, the problem with using old nomenclature for new ideas is that everyone's got a slightly different way of looking at it. And I try to cleave to the Department of Energy definition of a microgrid, which is something that can use local power in its circuits, but can also connect to the greater grid or disconnect from the greater grid. So I think of that as a microgrid. I think of a nanogrid as really like something you have going on in your laptop, where you've got battery storage, you've got a power input, you can disconnect from your battery, or rather you can disconnect from the power input and operate on your battery without losing your operations efficiency. So I like, for a campus mini grid, for a building microgrid, and for a device nanogrid.
So we're looking at a mini grid for the campus.
Think so. Yeah, it's like the regular grid, only mini.
So microgrid for buildings, mini grid for campus, nanogrid for appliances.
Yeah, that's
okay. Yeah, we want to be on the same nomenclatures. So I mean, again, so in the mini grid, what we're trying to do is to achieve efficiency by all of our power generation, right? So when some buildings are not in use or off season, can we shut everything down automatically with a controller? Or, you know, when people aren't using the building, if they're out and doing research for 8 hours a day, can we shut everything off?
Well, your occupancy sensors should do that for you passively for both lighting.
Aren't you generating power in an outlet? It's not, even if nothing's plugged in, isn't there still power going to that outlet?
No, because my outlet is connected to the PhD. So
your outlet.
Yeah.
Okay. But a typical AC outlet, right, that's in this room, there's power going to it even though nothing's powered plugged into it.
Unless it's got a relay, like if you were all in a building in California, the rule would be Title 24 in an educational building like yours, and it would be connecting 20 amp relays to your aux sensors, so you'd be turning off the outlets along with the lights when you left.
Okay.
So if I may just introduce a little bit of philosophy here, the big picture for you all in undertaking this design is really about, in my view, taking advantage of a asynchronous power system instead of a synchronous one. Does anyone have any idea of what I might mean by that, synchronous versus asynchronous?
No.
Well, Paul, don't jump
No,
ahead.
I'm
A lot of bright people in the room. Who's got synchronous versus asynchronous on the top of their head? All right, all right. So the grid, you know, the rate of speed that the alternating current goes from positive to negative is expressed in hertz, and the profile of the power that's going into your building and the power that you're using today as alternating current has to be precisely the same as all the rest of the power in your utility service area. It's called frequency, and it's all got to be the same. In the kind of power distribution system that you're considering, it is asynchronous. There is no requirement for your power to be alternating at the same frequency as your neighbor's power, because it does not alternate. Your electrons are going in one direction. And this is a huge benefit to your system, because you can bring distributed generating resources in by just matching the voltage. You don't have to worry about the frequency. And this is a massive advantage that you have in your asynchronous, AKA DC power system. You don't have to sing the song of a utility or a specific generator. You can mix and match across sources and loads as long as you've got the voltage right.
Okay, thanks. What's your integrated sky control system?
I'm sorry?
Your integrated sky, SKY.
Yep. So that's what we call the wireless control systems that we prefer to field our systems with. We can do it with Zigbee. We can do it with BACnet. We could do it with something that you're investing at school today. But we think that our Sky network, which is our label for an IPv6 wireless communications protocol, that being the next generation of Wi-Fi, is the best choice for wireless comms, because it's got the largest community program associated with it.
Yeah, I'm looking through my questions. Anybody else have any? You're aware of the diagram you have on your website? It's called the campus.
Yes.
Large-scale campus approach. Basically, I'm looking at that diagram, and it seems like we're doing everything there except grid control, everything in red. I can bring it up on the screen if you want to see it.
Okay.
Can you see that?
Yep.
I mean, what I like about that is it kind of gives us an idea of the overall campus configuration.
Yep.
But I don't know what on this diagram we wouldn't need or we're missing. Obviously, we don't have HVAC equipment.
Yeah, so that's a one-line diagram, which is doesn't have a lot of detail in it, but it does describe that common bus architecture to which you're adding or can add solar. And really, all of the elements of that are modular in the sense that you could develop an all DC network of any size.
So how would you suggest we work with our electrical department and Nick here, and how the electrical department could help us?
Is that the facilities electrical department, or is it the educational department?
Design, right?
Education.
Education.
Well, there's
design,
a lot of ways
right?
we could work together. We work with the UC system. We're on 5 of their campuses where we've done student teacher, PhD student teacher, student programs that involve the student body and what we're up to. If the question is how we would work with them on this project specifically, it would probably be in development of the drawing and the load calculations. There's going to be a lot of effort that has to go into the load schedules for each building and then the island as a whole, right?
So we're at the stage right now where we're collecting data on the infrastructure requirements of the island or the campus, let's say, right? So that's electrical requirements, water requirements, even food requirements. Solid waste, we're looking at solid waste conversion to fuel, waste to energy systems. And so that's going to kind of dictate adjacencies and size of buildings, size and location of buildings. We have maybe roughly 25 buildings, phase 1 and phase 2. And we do have a limited, you know, we can't, as I said, we can't clear cut. So we're kind of dotting things around as necessary. So when they get the layout, would that be a good time to interact?
Sure. Are you going with composting toilets or some kind of?
Yep. Everything on island right now is composting toilets.
Yeah.
And we may go to a centralized or more of a decentralized sewage treatment system where we can collect more compost and generate. You know, there's a system which I used in Abu Dhabi, which has photovoltaics, which produce the energy to automatically wash the cells, keep them clean and cool, and then that water drips down. The gray water then drips down after it washes off the PV panels into a reed bed system. And then the reed bed organisms are cleaning the sewage, and then it goes into a filtration system and UV light for purification. So we might look at those systems, but right now it's all composting toilets.
Yeah, I can't imagine you're going to have the same kind of sand filming problems in Belize that you had in Dubai.
No, probably not. But it's important to keep the cells clean and cool, right?
Yeah, but that's what you have graduate students for. So why don't we reconnect when you've got the beginning of your load calculations, your electrical load calculations. That'd be, I think, a natural time to reconnect. I will send you an intro call to Wayne Gutchow so you can quiz him on his DC powered water filtration experience. Okay. And I'm glad to make the acquaintance with all of you, and I'm excited that you're going to have a retrofit of your whole building there into modern technology soon.
Yeah, well, it's going to be, the good news is it's going to be built. I've been working with the owner for over 2 years on the island, and the hope is to get the students down there to actually build it.
Great.
All right, thanks, Paul.
Yep, thank you. Thanks, everybody.
Anybody have any follow-up questions? So what do you think?